Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 24 of this course of machine learning for earth system science. We are still in module 3 where we are exploring different applications of machine learning to answer various questions in and discover various insights in various aspects of earth system sciences. So today's lecture is going to be on nowcasting of extreme weather events. So earlier we had discussed what are extreme events. We had seen how to discover such extreme events like say tropical cyclones, etc. Today's task is nowcasting of such events. Now what is nowcasting? Nowcasting is the task of forecasting at short duration or at short notice. Of course what is meant by by short notice depends on the scale of the process. So if the extreme event, so in particular today we will consider two kinds of extreme events. One are heat waves or cold waves, and the other is lightning. Now heat waves and cold waves, these are basically things that last for several days, so a nowcasting of them should be done a few days in advance. On the other hand, lightning is a momentary phenomena, and so nowcasting of lightning should be something which is to be done maybe a couple of hours ahead of time and so on. Now the concepts which we are going to cover today are identifying precursor weather patterns before extreme events. That is, suppose an extreme event is going to happen, does the are there some weather patterns which which indicate that such a thing is going to happen? Can we mine or discover such weather patterns? Secondly, the spatiotemporal patterns can be used as inputs and outputs to machine learning models. So the kind of predictors which we will be considering in this case are mostly going to be spatial maps rather than observations at a particular location or at a particular time point. So we will need most of the models which we or machine learning models that we are familiar with, they take maybe a vector as input and so on, but in this case the input is a map. So in our when we are discussing various machine learning models, we had considered things like convolutional networks for spatial input and so on. So somehow we have to utilize those properties. And thirdly, the third concept we will see is how machine learning models can be used to emulate various process models. So process models we have seen earlier also. We are just in the previous lecture we were talking about the CMAQ model. Earlier also we had talked about other process models. So the today we will briefly talk about if machine learning can somehow be used as a surrogate for them. So of course this concept will come back in greater details in the 5th module. But now in this lecture, first of all let us start off by defining what are extreme hot and cold events. So what is a heat wave? Heat wave, we have all heard of heat waves. A heat wave is a prolonged stretch of high temperature anomaly at a location. That is, whatever is the expected temperature based on climatology at any given location, if the temperature remains significantly above that for a significantly long duration, then we say that is a heat wave. So obviously some concept of threshold is involved here. So how long and how much above climate threshold, etc. So various standard definitions are used in different parts of the world, which may be higher than 3 Kelvin above the climatology or above the 99th percentile. For again, for how many days, this also can vary. Maybe in some countries they may use 3 consecutive days, some other countries they may go for 5 consecutive days and so on. And whenever we are talking about this anomaly or the percentile and so on, I mean the amount of anomaly of 3 Kelvin or the 99th percentile, these are specific to location and the day of the year. Say for example, if the temperature is say 31 degrees Celsius for 5 consecutive days in May, that's probably not a heat wave, because it is actually expected that the temperature will be 31 or higher than that in that period. But if the temperature is 31 degrees Celsius or more for 5 consecutive days in December, then that's a big thing, because in December the temperature is expected to be lower. So these things are these are usually not absolute, but they are specific to location and also the time of the year. So what is a heat wave in Rajasthan may not be what is a heat wave in Ladakh may not be a heat wave in Rajasthan. Similarly, we can define cold wave also analogously by consider, instead of 99th percentile, if we consider the 1 percentile, or instead of higher than 3 Kelvin, if we consider lower than 3 Kelvin, and so on. So the target variable in this case is the air temperature 2 meter above the surface. This is what the variable which we will be focusing on to understand whether heat wave, cold wave, etc. is happening or not. And the predictor is in the paper, of course there can be many variables which can be predictors, but in the paper that we are going to study, they have considered only one predictor, that is geopotential height at 500 HPA. So that basically it's we know that the pressure varies with altitude. So a particular pressure, say 500 hectopascal, at what altitude will that be attained? This is the variable. So it is on an average this is 5.5 kilometers altitude, but it varies from location to location and also from time to time. So that is called the geopotential height. It can fall to maybe 5 kilometers or rise to 6 kilometers and so on. So this is the paper where the analog forecasting of extreme causing weather patterns using deep learning. So note the choice of words in the heading, extreme causing weather patterns. So extreme causing, so they are assuming that there are certain weather patterns which cause extremes, and those weather patterns are mostly related to this geopotential height as they have considered in this paper. Numerical weather prediction models require ever-growing computing times and resources, but still sometimes have difficulties with predicting extreme weathers. We introduce our data-driven framework that is based on analog forecasting or predicting using past similar patterns, and employs a novel deep learning pattern recognition technique called capsule neural networks and an impact based auto leveling strategy. Using data from a large ensemble fully coupled earth system model, CAPSnets are trained on mid tropospheric large scale circulation patterns of Z500. Z500 basically means the geopotential height at 500 hectopascals, labeled 0 to 4 depending on the existence and geographical region of surface temperature extremes over North America several days ahead. We will explain this in the coming slides. The trained network predict the occurrence or regions of cold or heat waves using only Z500 with accuracies of these numbers, which are reasonably high, 1 to 5 days ahead. Using both surface temperature and Z500, accuracy increased to 80% in both cases. CAPSnets outperform simpler techniques like convolutional neural networks and logistic regression, and their accuracy is least affected as the size of training set is reduced. The results show the promises of multivariate data-driven frameworks for accurate and fast extreme weather predictions, which can potentially augment numerical weather prediction efforts in providing early warnings. So the basic approach of this paper is as follows. So the idea is that there are some large scale weather patterns, that is the spatial maps of variables, which may be visible before an event. Before an event means, in this case, 3 to 5 days before the event. The approach here, first of all, use clustering or k-means to identify similar spatial patterns. So, this is actually used this clustering is not part of the prediction algorithm, but this is used for labeling purposes. So, like there is a huge amount of data which they have to label, that is they have obtained the data set basically from some kind of model simulations. So, that is a huge volume of data, but for training any prediction algorithm you need labeled data. So, like since we cannot expect a human being to sit and label so many like so many pieces of data. So, what they have done is they have used auto labeling strategy, which means they first do the clustering of the data. The clustering is so I will show you like the clusters. So, these are the examples of the cluster. So, you can see it's the clustering is done of both the air temperature as well as the geopotential heights. So, this is what like if you do the clustering, this is what, so this is actually the temperature, not the temperature itself, but the temperature anomaly. So, here you can see that each cluster is basically some kind of a spatial distribution of the temperature anomaly. So, here you can see like there is a strong positive temperature anomaly in this region, in the like in the you can say the what is known as the Midwest region, while in these regions there seems to be a like a cold wave kind of thing. This is the second cluster where we see the strong positive anomaly in this region. In S3 there we see the weak anomalies mostly, while in S4 we see a strong positive anomaly along the eastern coast, while in there is one more pattern which does not show any significant anomaly in any place. And similarly, if we do the clustering of the geopotential heights, there also we see of course all these patterns are roughly the similar, unlike in this case, but there are subtle differences also. That is, as you can like if you look at the maps, you can understand the differences of these contours. And so, this kind of clustering is actually used. So, like this is in summer and this is in winter. So, these clusterings are used for prediction of heat waves and these ones for the prediction of cold waves. So, these clusters are created for the purpose of labeling. That is, like every spatial map is to be labeled as like this is going to be like this is a heat wave in this part of the country, this is a heat wave in that part of the country, or this is not a heat wave at all, and so on. So, now some of these patterns are which we obtain by this kind of Clemens clustering are associated with heat or cold waves in particular regions, as we just saw in the examples. Now, the operation of the prediction algorithm is as follows. So, every day's spatial map of Z500 is presented as an input to the machine learning model. In some cases, along with Z500, that day's air temperature also may be presented as an input, and what the model is going to predict is whether there will be an extreme event after 3 days, and if so, in which region. I mean, not point wise, I mean not at exactly in this city there is going to be a heat wave, not something like that, but in general, is it the northeastern region or is it the south central region or which region, the broad region that they can predict. And the spatial input is presented through the machine learning model. So, the machine learning model should be such a model which is capable of taking in the spatial input. So, like we had discussed about convolutional neural networks for spatial models earlier. So, in this case they use a more sophisticated version of that, the capsule neural network. So, just to illustrate this, so this is the training purpose. Here they have shown the labeling, where like basically they have all the maps the spatial maps of the different variables obtained from either the observations or simulations. So, for labeling purposes they have utilized this clustering technique which we mentioned. So, that way they get this kind of the labeled data, that is every map is accompanied by a label, which means like whether it is followed by a heat wave or not, and if a heat wave, then a heat wave in which region. Now this kind of labeled data is presented as CAPSNet. It is used to present a CAPSNet. So the input is the spatial map of a like of the geopotential height, and the prediction is going to be like any of these 5 classes, right. So like this is the test input, the geopotential height map, and the the question that is being asked is, will there be a hot spell or cold spell in 3 days, and if so, in which region? And this is what the output is going to be like, that it seems that this pattern is a precursor to a W3 kind of event. W3 basically means a cold wave in the northeastern part of the country. So now what is this capsule neural network? So the capsule neural network is a like a special kind of convolutional neural network which has all the components of the convolution, such as the convolutional layer, the pooling layer, etc. However, all these convolutional input units, these are used to develop what are known as the capsules, and these capsules are then there is a hierarchy of capsules like that, and all those capsules are arranged in a particular way, and based on the arrangement of those capsules, finally the class prediction is made. The reason why people use capsule neural networks is especially to preserve the spatial alignment, which unfortunately convolutional neural networks are not always used to are not able to identify. Like in case, suppose there is an input is presented in front of a convolutional neural network which has all the features, but not in a specific spatial layout. Say like for example, when we consider a human's face, it is expected that the eyes will be on here, then followed by the nose, followed by the mouth, and so on. But if there is a if an image of a human face with the one eye here, the nose on top, etc. I mean basically all the features are present, but they are misaligned. The convolutional neural network will still think that it is a human face, which of course it is not. So this kind of a problem, however, can be avoided with a capsule neural network, which actually defines some kind of a spatial ordering of the different features that are being represented by the different layers of the neural network. So these are the results which the prediction results which they get, the accuracy as well as the recall, and they show the accuracy at different days ahead of time. So obviously we can say that 1 day before the heat wave or cold wave we can expect higher accuracy, then after 2 days ahead we can expect slightly lower accuracy, and so on. So this is that's the effect we see here, but we show that in the case when these capsule neural networks are used, then in all days or at all lead values, we find that the accuracy is highest compared to other approaches like say convolutional neural network or linear regression, logistic regression. So since this is a classification problem, we can also use non-deep methods such as logistic regression, but we find that its prediction is not so great. And the reason for that obviously is that these convolutional or capsule neural networks, they are able to take the spatial map as input, and it's actually able to represent the spatial relations, which something like logistic regression, which considers the whole thing as just as a long vector, is unable to do that. Not only that, it is found that the capsule neural network also does the best with least amount of training. So training examples, even if you use the only 25% of the training samples, then also its performance is better than the others. So that is so this is one of the papers we are discussing. The second one is related to, as I said earlier, lightning prediction. So the question here is, can we predict when lightning is going to take place a few hours ahead of time? And the usual approach to do that, the way meteorologists have been dealing, is run process based simulation. So there is a WRF model, it's a numerical weather prediction model, which is also known as NWP. Like there is a set of numerical equations which it has to solve at various grid scales to do the simulation. So it takes like at any given point the current weather is including all the different variables is provided as the initial condition, and it is allowed to run for a specific duration of time, and then it produces the the outputs. Now the problem is that this is time and resource consuming, but can the machine learning models identify the spatial maps of variables as precursors, so just like in the previous case. So like in this case we will need inputs from the WRF itself, as well as we will need some observational inputs. So and all these inputs are going to be in the form of spatiotemporal map, not just spatial maps but also spatiotemporal maps. In the previous case we just had one single map, but in this case we will need a series of or a sequence of such maps. So lightning is a natural phenomena, poses serious threats to human life, aviation and electrical infrastructure. Lightning prediction plays a vital role in lightning disaster reduction. Existing prediction methods, usually based on numerical weather models, rely on lightning parameterization schemes for forecasting. So it's the lightning is not directly forecasted by the models like WRF, but certain enabling conditions are known due to some other variables are known which are considered to be the immediate triggers to lightning. So when we are running the NWP, we keep track of certain variables, and whenever those variables they reach some specific values and they are combined using some kind of a parameterized relation, then we understand that a lightning is likely to be triggered. So these methods, however, have two drawbacks. Firstly, simulations of the numerical weather models usually have deviations in space and time domains, which introduces irreparable biases to subsequent parameterization processes. Secondly, the lightning parameterization schemes are designed manually by experts in meteorology, which means these schemes hardly benefit from abundant historical data. In this work, we propose a data-driven model based on neural networks referred to as LightNet for lightning prediction. Unlike the conventional prediction methods, which are fully based on numerical weather model, LightNet introduces recent lightning observations in an attempt to calibrate the simulations and assist the predictions. LightNet first extracts spatiotemporal features of the simulations and observations via dual encoders. These features are then combined by a fusion module. Finally, the fused features are fed into a spatiotemporal decoder to make forecasts. We conduct experimental evaluations on a real-world North China lightning dataset, which shows that LightNet achieves a threefold improvement in equitable threat score for 6-hour prediction compared to 3 established forecast methods. So like when we are doing conventional lightning prediction, this is the way it happens. So first of all, like there is the database of historical weather collections. Based on that, numerical weather prediction is initialized, and it is used to run the simulation for the future, say the next 6 hours or something like that. Now as I said, as the simulation runs, certain variables which are known to be triggers of lightning, known to experts, those variables are tracked, and based on them there is some kind of lightning parameterization which on the basis of those variables keeps calculating the probability of lightning at any given location and time. Now the way this paper hopes to improve is by bringing in recent lightning observations along with the simulations of these various geophysical variables, and developing this kind of a lightnet model, which in a sense is able to bypass the simulation. I mean the simulation cannot be completely done away with, but this lightnet model, it will in a sense it will keep receiving the inputs from the simulations and as well as the past lightning data, and it will be making the predictions. So the need of this parameterization is largely done away with. Now as I said earlier, just like the previous paper, in this case also the inputs are going to be special maps of the different variables which are obtained from the simulations as well as the historical distributions of the lightning. So so once again we have the special maps as input, so we will need some kind of convolution at the input. The outputs are also going to be like these special maps, because unlike in the previous paper where the predictions were like just a few discrete values, like in fact only 5 discrete values, in this case we actually want an output as a special map, where we want to provide at every location, at every point, I want to give a probability of that a lightning may take place there. Okay. So like at both the input and the output we need convolution, and besides at the input we have a sequence of spatial maps coming in. I mean, as the simulation is running in the WRF, the spatial maps of the different variables, those are also coming in at every point of time. So we have a sequence of spatial maps as the input, unlike the previous case where we had only a single like spatial map as input. We have a sequence of spatial maps as input, so we need something like a conv LSTM for the temporal part and convolution for the spatial part. So conv LSTM is like it's a method that was developed in 2015. So the idea is that it is such an LSTM where the inputs are not usual vectors as in a normal LSTM, but they are matrices or tensors. And the like whenever in a normal LSTM, whenever there is the usual matrix or vector multiplication, that is replaced by this convolution operation. So this is the scheme of the whole thing. So there is a WRF encoder which encodes which receives in the spatial maps from the WRF simulation, and there is an observation encoder which receives the like the lightning distribution as I mean the spatial map of lightning as the inputs. So these two things are separately encoded by two separate networks, and then the encoded versions are somehow fused using a fusion module. So this is like basically some kind of a concatenation operation followed by convolutions. Now, so finally what we get is an encoded form of the past lightning as well as the simulations of the different weather variables, and these are then finally used for the decoding purposes. So like at both the encoder at the fusion layer as well as the decoder, the convolution is used quite heavily, as you can see. So so these ST, IT, GT, RT, VT, so these are basically the inputs which we get from the WRF at any given time. So they are stacked together to form PT, like a combined form, and then this they are passed through convolution of a convolution layer, and then followed by a conv LSTM. So we have a sequence of these things, so they are present into the LSTM. So the output of the LSTM is the CWRF and HWRF. So it's in a sense it's like the encoded hidden state of the sequence of maps that we receive from the WRF. Similar steps are done in the observation encoder also. So from there also we get these C and H maps. So C and H for our LSTM of course refers to the cell state, I mean the long term and the short term memory, as we have discussed in the lecture on LSTM or the sequential models. and then there is a fusion layer in which all these these things are fused, they are stacked together, concatenated together, followed by convolution, and then this thing is used as input to the decoder, which once again utilizes convolution to produce the output. So, like these are the results which of this. So, like when we are making pointwise forecasts of something like lightning, or rather nowcast, it is usually evaluated using certain metrics like POD, the probability of detection, that is suppose a lightning actually happens, what is the probability that I will be able to for nowcast it, that is POD. Next is false alarm rate, which is of course self-explanatory, and then there is ETS, or equitable threat score. So, like when I am successful in making a prediction, it might have happened by chance also. So, can I somehow estimate how much better I am doing rather than just random predictions? And so, like this is what the predictions may look like. So, like we can say that 3 hours ahead of time, these are some of the like the recent observations of the lightning. So, these blue point, these are like the distribution of lightning events at different locations, and then based on that, in the coming hours we make a map. So, at every location we actually plot the probabilities of the lightning happening or not, and so like what these different colors indicate is the observation, prediction, and the hits. So, the blue means like lightning is observed, green means it is predicted, and red means hit, means both observed as well as predicted. So, as you can see that at least for the first 2-3 hours there is a significant number of hits over the spatial field. So, these are the different papers which we discussed today. This is the first paper and about the heat wave prediction, and this is the second one about the light net, and for convalescentium, which this is here is the paper. So, the key points from this lecture are, first of all, the spatial and temporal maps of variables may be precursors to extreme events. Secondly, the machine learning models can predict such events by identifying certain signature patterns, and convalescentiums or capsule neural networks, these are suitable to identify like the spatial patterns. So, so of course, because the inputs are spatial maps, so we need convolution, but in both cases we are going beyond convolution. In one case we are going capsule neural network, which like considers the spatial ordering, and then there is convolution LSTM, where we have which are for receiving a sequence of spatial maps. And it is important to work alongside the process models such as the WRF in such cases, and like the machine learning can also be used to emulate these kind of process models. This is again a point which we will see in greater detail in the coming slides. So, that brings us to the end of this lecture. We are nearing the end of the current module, which and in the coming lecture will be the last of this module 3. So, till then, bye.